Okay, today is still about the inverse of a matrix. Take a review about the definition of the inverse of a matrix. Suppose a matrix A is square matrix. Here we don't consider the inverse of a rectangular matrix. A is a square matrix. Say the size is n by n. The matrix A has inverse. That means if you can find some also square, also the same size, some n by n matrix C such that A times C is identity matrix, and also C times A is identity matrix. Then we say that this matrix C is the inverse of matrix A. The notation is denoted by this notation, A to -1, A to -1. When matrix A has an inverse, we say that A is invertible, or a second term. This second term we also often use non-singular. Yeah. A matrix A is non-singular. That means that the matrix has inverse. Yeah, this is definition. If you can find a C so that these two equations hold, then A has an inverse. Theoretically, it has been proved. It has been proved that a matrix times A is I if and only if A times C is I, if and only if C times A is I. So these two equations, you only need to make one true. The other one is automatically true. So you don't need to check these two equations. Just check one of them. Okay. Yeah. This is a remark A. Remark B. For a 2x2 matrix, it is very easy to tell the matrix is invertible or not. That is a theorem. The theorem is here. Let A be 2x2. Then, how to know this matrix is invertible? Have a check with this quantity. A times D. The product of the diagonal entries minus C times B, the product of the
diagonal entries. If this number non-zero, then A, this matrix is invertible. Okay. And its inverse is this, given by this equation. 1 over this number, A D minus CB times D negative B negative C, then A. Yeah, this matrix is the inverse of A. On the other hand, if this number is 0, A is not invertible, or A is singular. Okay. Let me separate. Yeah. A is singular. Yeah. We usually call this number, give a name to this number, determinant of matrix A. Yeah, this number. Yeah, this number determines if matrix A is invertible. This is a review about some key points from the last class. Remember the definition. Okay. Now, topic 1. I want to show you more examples about the inverse of a matrix. Take a look at the following example. This is a topic 1. Consider this linear system to 3x1 4x2 is 2. It's 3. And 5x1 plus 6x2 is 7. 3 questions. A, write the linear system in matrix form, in the form of a matrix times the vector of the unknowns, of the 2 unknowns, and then equals to right hand side. Okay, solution. Then how to write this linear system as AX equals to B. A is coefficient matrix. Coefficient matrix is first column is the coefficients of the unknown x1, 3, 5. Second column, the coefficients of the unknown x2, 4, 6. Yeah, this is a coefficient matrix. The unknown vector consists of the 2 unknowns, x1, x2. Right hand side, the right hand side vector is consists of the numbers on the right hand side, 2 numbers, 3, 7. Yeah. Then this is A, this is X, this is B. Yeah, this equation is this linear system. Okay. Second question. Is the coefficient matrix invertible? We need to use this theorem. Yeah, the theorem here. Because the coefficient matrix is 2 by 2, therefore we can use this theorem. Okay, now we have a check with the determinant. Okay, determinant. Okay, now to answer this question, let me compute the determinant of matrix A. Determinant by formula, it is diagonal, the product of the diagonal entries, 3 times 6, minus the product of the n-time diagonal entries, 5 times 4. Let me see whether or not this number is 0. 3 times 6, 18. Then minus 20 are non-zero. So because determinant is non-zero, so A is invertible. It has an inverse. And the inverse, we also have a formula for the inverse. Yeah, the formula is here. Yeah. 1 over determinant. 1 over determinant. Now determinant is -2. Then times, let me see. D, -B, -C, and then A. Okay, D. Now D is 6. -B. This is a B. -4. -C. -5. And then A here. A is number 3. So 3. Number 3. Now, a number times a matrix is the number times all the entries. So -1/2 times 6, -3. -1/2 times -4. Number 2. -1/2 times -5, 2.5. And then -2. -1/2 times 3, -1.5. Yeah. Inverse is this matrix. Okay, now question C. Question C. Solve the linear system. Okay, now solution. Solve the linear system. Solve. Linear system is AX is equal to B. Now I solve it. Because we have inverse available. So I multiply this equation from the left side by A inverse times A, both sides, A times -B. Yeah. All right. A inverse times A is identity matrix. So therefore, we have identity matrix times this vector is A inverse B. But identity matrix times any matrix is that matrix. So I times X is just X. Yeah, just X. Yeah. Okay, now I compare this matrix times this vector on say here. I compute again here. So it is equals to A inverse. This matrix is A inverse. -3, 2, 2.5, -1.5. B, yeah, this vector. So times 3, 7. A matrix times a vector is a vector. Yeah, 2 by 2 times 2 by 1. The result is 2 by 1. So the vector is first row times the vector. -3 times 3, -9. Then plus 2 times 7, 14. And then 2.5 times 3. 7.5, right? And then minus -1.5 times 7, 10.5. So this is a 5. How about here? -3. So the the solution is 5, 3. That means that x1 is equal to 5. x2 is equal to 3. Yeah, this is the solution of this linear system. Linear system. Yeah, linear system. Okay, for a 2x2, for a 2x2 matrix, we can determine if the matrix has an inverse by looking at this number. Then, how about for a general matrix, general n by n matrix? How to tell the matrix is invertible? The theorem is the following. Okay. Yeah. Let me present the theorem here. For a general matrix, then we have this theorem to tell the matrix is invertible, whether the matrix is okay. N by n matrix A is invertible if and only if A is row equivalent to the identity matrix. Here, row equivalent. That means that we can apply a sequence of row operations to reduce A to identity matrix. If you can reduce A to identity matrix, then matrix A has inverse. The reverse also true. Matrix A has inverse, then the matrix A must be reduced to identity matrix. This is what this theorem says. The proof, not difficult. Yeah, let me try to prove. Okay, proof. Okay. There are two directions. Let me prove this direction first. This direction means suppose A is invertible, then A can be reduced to identity matrix. Okay. Suppose A is invertible, then this linear system, homogeneous linear system has only 0 solution. How to see this? How to see this? Because A is invertible, that means that A has inverse. I multiply A inverse to the both sides. Then A inverse and A cancel. So the solution is this. But any matrix times 0 vector must be 0. So if A has inverse, then this homogeneous linear system only has 0 solution, no non-zero solution. Okay, this linear system has low non-zero solution. That means that all the unknowns are basic unknown, low free unknown. Wait. So linear system has no free variables, right? If homogeneous linear system has a free variable, then it has infinitely many solutions. Now only one solution, so low free variable. Okay, so the columns of A all are pivot columns. All are pivot column. Each column of A contains a pivot. So that means that A can be reduced to its epsilon form is each column has a pivot and the matrix is square. So the epsilon form of A must be in this form. Epsilon form must be this. All the pivot numbers are on the main diagonal line. Okay. Yeah. Suppose that A is n by n. Yeah, this is a n by n. N by n. So epsilon form also n by n. Now there are n pivot numbers. Okay. Okay. Now I further. This is the black square is non-zero. I can use the black square to perform backward elimination to zeros to eliminate the entries above. So, and then, yeah, I can use these non-zero numbers to make the numbers above all zero. All zero. All zero. Now, finally, scale each row. Then I get identity matrix. Identity matrix. This is an identity matrix. One. Yeah, this is an identity matrix. So if A has inverse, then this linear system has just one solution, the zero solution. In other words, the linear system has low free variable. Low free variable, that means that all the columns of matrix A are basic column, low free column. Basic column means the column contains a pivot number. So the epsilon form of matrix A must be in this form. Now I can use the non-zero number on the main diagonal line to eliminate the numbers above. So to get this epsilon form. Finally, scale to get identity matrix. Therefore, a matrix A is invertible, then A can be is row equivalent. Row equivalent again means can be reduced to identity matrix. This is one direction. Now, second direction, the other direction. Suppose A is row equivalent to identity matrix. Then this matrix A must have an inverse. How to see? Solve this equation, matrix equation. Yeah. A n by n, x n by n. This is an identity matrix n by n. If I can find one solution, then by definition is here. If I can find some n by n matrix such that this equation is true, then matrix A has inverse. Now, I solve this equation. If I can have a solution, then A has inverse. Okay. How to solve this matrix equation? For augmented matrix. Form augmented matrix. augmented matrix is coefficient matrix together with right-hand side. Okay, now we are given that matrix A, we can perform a sequence of row operations, reduce A to identity matrix. Now I perform a sequence of row operations on this augmented matrix. Then step by step, then we will get A becomes I. But this I will become submatrix. Yeah, this is the reduced epsilon form of this matrix. Now the final matrix here. Okay. The final augmented matrix is the following equation. Coefficient matrix times the unknown is equal to C. X is a matrix, C is a matrix. Identity matrix times unknown matrix is the unknown. So the unknown actually is this matrix C. Yeah, this is the solution of this equation. So when A can be reduced to I, then this matrix equation has a solution. The solution is C. So therefore, I can find a matrix so that this equation, so therefore, yeah, the matrix here actually is a solution. Therefore, A times C is I. So A has an inverse. In other words, that is A is invertible. Yeah, done. The proof is done. So this theorem, okay, for 2x2 matrix, we can use this theorem here. The theorem in the review. For n by n general matrix, how to know the matrix has inverse? Use this theorem. If matrix A can be reduced to identity matrix, then A has inverse. Otherwise, A has no inverse. Let me show you examples about the theorem we just learned. Okay, yeah. Here, example 1. Determine if the following matrix invertible. Okay. The matrix is this: 1, -2, -1, 3 by 3. Hey, 3 by 3. So I use the theorem we just learned. Let me find epsilon form of this matrix. Reduce A to epsilon form, step by step. Perform a sequence of row operations, then I get epsilon form is this. This is the epsilon form. Epsilon. Can you further reduce this matrix? Question mark. Can you further reduce this matrix to identity matrix? Identity matrix. I don't think so. Why? Because here in this position, the entry is 0, not non-zero. I cannot use this 0 entry to eliminate the zeros above. Therefore, because this entry is 0, we cannot further reduce this epsilon form to identity matrix. So the answer is no. So therefore, conclusion, because we cannot reduce A to identity matrix by field. So answer, conclusion is A is not invertible. This matrix has no inverse. So done. Example 2. Let me change the matrix A a little bit. Say, let me change this number from 5 to 4. Then the matrix has inverse. Okay, now second example. Example number 2. Determine if the following matrix invertible. The matrix is 1, -2, -1, -1, 5, 6, 5, -4. Now here, not 5, but 4. Okay. Now see, let's see whether this matrix has inverse. Reduce this matrix to epsilon form by forward elimination. Perform a sequence of operations, then the epsilon form is 1, -2, -1, 0, 3, 5, 0, 0, -1. This time, because each column is a pivot column, I can use the pivot, pivot number, pivot. I can use these 3 numbers to create zeros above. And finally, scale each row. Then I get identity matrix. Yes. Identity matrix. This is an identity matrix. So conclusion is A by field is invertible or a second term, non-singular. That. This matrix is non-singular. This is the first topic about the inverse of a matrix. Now the second topic, how to compute inverse. Given a matrix, the matrix is invertible. How to find the inverse? Topic 2. How to find inverse? We need to go back to the definition. Definition is here. How to find inverse? We need to find a matrix C. So that either of these 2 equations, one of these 2 equations is true. then the C is the inverse. Okay. How to find inverse? Solve this matrix equation. Okay, for X. Yeah. A, suppose n by n, X n by n. Identity matrix n by n. Solve this equation. If has solution, then the solution is A inverse. How to solve this equation? Form augmented matrix. A coefficient matrix together with the right side. Then reduce this augmented matrix to identity matrix. Okay, perform a sequence of operations on this matrix. Then step by step change A to I. At the same time, I identity matrix will be changed to some matrix. Then the final augmented matrix is this matrix equation. So I identity matrix times the matrix is the matrix itself. You see. So this matrix here is the solution of this equation, and this matrix is the inverse. Okay. Okay. All right. So in summary, let me make a summary. In summary, how to find A inverse? How to find A inverse? Step one. Step one. Form this matrix. Put A here, then put identity matrix here. Okay. Step one. Step two. Perform row operations to reduce this matrix to a matrix of this form. Here, identity matrix. Then here, A is reduced to I. At the same time, I is reduced to some matrix, say C. If successful, may not be successful. If successful, if we can reduce this matrix to a matrix of this form, then C is the inverse of matrix A. Then A inverse is equal to C. Yeah, this part is A inverse. On the other hand, if not successful, if not successful, then A cannot be reduced to I. That means that A is not row equivalent to I. By theorem, A has low inverse. A has low inverse. We don't need to find its inverse. So stop here. If A cannot be reduced to I, A has low inverse. So we don't need to find its inverse, low inverse. So 2 steps to compute the inverse of a matrix. Step 1, form augmented matrix. Reduce augmented matrix to a matrix of this form. If successful, then the matrix here in this part is A inverse. If not successful, A has no inverse. Let me show you examples about these two steps. Example one, say here. Example one. Find the inverse of the following matrix. The matrix is this: 0, 1, 2, 1, 0, 3, 4, -3, 8. Okay. Find the inverse of the matrix. The matrix may not have inverse. So here, let me add. If the inverse is 6, if the inverse is 6, find the inverse. Otherwise, no inverse. Solution. Now, 2 steps. Step 1, form augmented matrix. Okay, now let me form augmented matrix. A together with identity matrix. Yeah, in detail, it is A. This A. Separate with the right side. The right side is identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Right side. Okay. Now, step by step, reduce this part to identity matrix. First, perform forward elimination to reduce the matrix to epsilon form, and then reduce epsilon form. Because the 1, 1 entry is 0, I cannot use it to eliminate entries below. So let me interchange the first 2 rows. Row 1, row 2, interchange. Then I get this matrix. Okay. Row 2, the whole row. Row 2, whole row. Okay. Now 1, 0, 3, 0, 1, 0. The whole first row. 1, 0, 1, 2, 1, 0, 0. Interchange 2 rows. And then the third row, not change. Yeah. Separate. All right, now I can use this pivot entry to eliminate the number 4. -4 times first row plus row 3. Put the result in row 3. So 1, 0, 3, 0, 1, 0. Second row, not change. But the third row is change. -4 times 1, add to 4, 0. -4 times 0, add to -3, -3. -4 times 3, -12, add to 8, -4. -4, right? Yeah. And then separate. Okay. -4 times the 0, add to the 0, 0. -4 times 1, add to 0, -4. And then -4 times 0, add to 1, 1. Yeah. Add to 1. All right, let me continue here. All right, further reduce this matrix to epsilon form. Now, next, I use this number to eliminate -3. Number 3 times row 2 plus row 3. Then put the result in row 3. Row 1 not changed, so copy row 1 here. Row 2 not changed. Now row 3 change. Positive 3 times 1 add to negative 3, so 0. 0. Positive 3 times 2, 6, add to negative 4, 2. Positive 3 times this number, 1, add to 0, so number 3. And then positive 3 times 0, add to negative 4, negative 4. Times 0, add to 1, so 1. Because there is a non-zero number here, non-zero number, non-zero number. So I am sure the matrix A can be reduced to identity matrix. Now, okay. Now further, how about let me scale row 3 first. 1/2 times row 3, then put the result in row 3. 1, 0, 3, 0, 1, 0, 0, 1, 2, 1, 0, 0. And then scale row 3 by 1/2. So 1/2 times 2, 1. 1/2 times 3, 3 over 2. 1/2 times this, negative 2. 1/2 times 1, 1/2. Yeah. Now, perform backward elimination. This time, I use this number as the pivot number to create zeros above. Let me see. -2 times row 3. Add to row 2. Put the result in row 2. Yeah, step by step. Okay, don't make mistake. This operation only change row 2. So let me copy row 1 here. Row 1 here. All right, now row 2 is changed. -2 times 0. Add to 0, so 0. -2 times 0, add to 1, so 1 here. -2 times -1, add to 2, so 0. -2 times this number, it is -3, then add to 1, so -2. -2 times this number, +4, add to 0, so 4 here. -2 times this number, -1, add to 0, -1. Yeah. Only row 2 is changed. Now copy row 3. Yeah, row 3. Yeah. Now the last step, use this number to eliminate this number. -3 times row 3, add to row 1 on next page. -3 times row 3, add to row 1. Put the result in row 1. This operation only change the first row. So the first row is 1, 0, 0. -9 over 2. 7. -3 over 2. Then 0, 1, 0. -2. Wouldn't 3/2 times -2 be not -2 where? -2. Oh, -2 times this number and -2 times this number -3. -3 plus 1, -2. I am correct. -2 times -2 times row 3. Yeah, I am correct. Okay, thank you. But anyway, thank you for your question. Yeah. Okay. Okay. Then here is 4. -1. 0, 0, 1. Row 3, no change. 1/2. Yeah. So matrix A, yeah, this part, coefficient matrix, is successfully transformed to identity matrix. Therefore, this part here, yeah, this part here is the inverse of the matrix. Yeah, here, yeah, this part here is A inverse. So therefore, the answer is, so conclusion, A inverse is -9/2. Yeah, -9/2. Then 7 3/2. Yeah. Yeah. That if the computation all are correct, this matrix, this inverse should have this equation: A times this matrix, original matrix times this matrix, should be identity matrix. You can have a check. If your result multiplied by A is not identity matrix, then in some step your computation is wrong. It's wrong. If all the computations are correct, we should have this equation. Okay, you can have a check. Okay, this is a example 1. Now, example 2. Example 2. Let A be 1, -1, 2/2. Okay, find A inverse. Because this a 2/2 matrix, we can use the theorem here to find inverse. And also, of course, we can use these 2 steps to find the inverse. So to answer the question, we have 2 solutions. Okay. Because the matrix A is 2/2. So solution 1. Solution 1. 2/2 matrix. How to know the matrix has inverse? First, compare determinant. Yeah, compare determinant of A. Determinant is product of the main diagonal entries 1 times 1 minus product of the anti-diagonal entries. It turns out that -1 times -1, 1. 0. Oh, A has no has no inverse. No inverse. So no inverse. We don't need to further find its inverse. No inverse. Now, solution B. I use this 2 steps. Try to find its inverse. Okay, form augmented matrix. In detail, A is 1, -1, -1, 1. Identity matrix 2 by 2. Yeah, let me try to reduce this augmented matrix to a matrix of this form, identity matrix, some matrix C. Okay, yeah. Okay. If successful, then C is inverse. Okay, now let me try. Okay, forward elimination first. How about 1 times row 1 plus row 2. See what will happen. Put the result in row 2. 1, -1, 1, 0. Okay. 1 plus -1, 0. -1 plus 1, 0. 1 plus 0, 1. 0 plus 1, 1 here. Because the entry here is 0, not non-zero. Therefore, I cannot further reduce this part to identity matrix. Okay. Since A cannot be reduced to I, by theorem, A has no inverse. No inverse. Done. Done. Yeah, to this example, there are 2 solutions because the matrix is 2 by 2. Yeah. This is topic 2. Okay. Let me see. Topic 3. Some properties about matrix A. I think today this topic is very short. I think I have time to present a 4 topic today. Let me add a 4 topic. 4 topic is 2.3. 2.3 is section only 1 theorem. Okay, only 1 theorem about the theorem is called invertible matrix theorem. Yeah, I think I have time to present the, this topic today. Okay, now let me present some properties about A inverse. Okay. Topic number 3. Properties about A inverse. Okay. These properties are very basic. Okay. Okay. Number 1. A matrix A. Take inverse on the matrix A. Then take inverse again. The result is the original matrix. Just like a number. Take inverse on the number. Then take inverse again. We get original number. Similar. Now B. A times B. Then take inverse. Some people may think the result is A inverse times B inverse, but wrong. Pay attention, okay? A times B inverse is equal to B inverse times A inverse. Okay. Reverse order, in reverse order. Yeah, pay attention. Okay, pay attention to this. C, I can extend property number 2 from AB, 2 matrices, to multiple matrices. Yeah. Matrix A1 times matrix A2 times how about matrix AP? There are P matrices. Then take inverse. The result is AP inverse times the second last matrix is A P minus 1 inverse times then times A2 inverse times A1 inverse. Okay. Reverse order. Remember, okay, remember. Okay. Property C. Property D. Property D. Okay. A matrix. Take transpose. Do you remember how to take transpose? A matrix. How to take transpose? Draw a line along the main diagonal entries. Yeah. Then rotate the matrix about this line. Okay. Take transpose on matrix A. A is square. Then take inverse. Oh, it turns out that it is equal to take inverse on A, then take transpose. Result. A take transpose first, then take inverse is equal to take inverse first, then take transpose. Yeah. We often use these properties. But let me add a warning here. Warning. Okay. A common mistake. A plus B take inverse not equal to A inverse plus B inverse. Yeah, I often see students make a mistake like this. Okay. Yeah. Say for example, a number. Yeah. 3 plus 7. You can view a number as a 1 by 1 matrix. Take inverse. It doesn't equal to 3 inverse plus 7 inverse. Right? This is the left side is 3 plus 7 is 10. Take inverse is 1/10. The right side is 1 over 3 plus 1 over 7. This is a common denominator. 3 times 7. So 10 over 21. Yeah, clearly 1/10 is not equal to 10 over 21. So for numbers, we don't have this equation. Even for a matrix, for matrices. Okay. So remember, this is a common mistake. I still have 10 minutes, so I can present topic 4. Topic 4 is section 3.2. Yeah. Topic 4, section 3.3, 2.3. Yeah, this section only one theorem. The theorem is called invertible matrix theorem. Yeah, this theorem. This theorem is a connection of properties, but not basic properties. Basic properties are these 4 properties. The theorem is a collection of properties that are often used about invertible matrices. Okay. Yeah. Okay. Now let me present the theorem. Theorem. The name of this theorem is invertible matrix theorem. Okay. Let, of course, A be square. Okay. Whenever we talk about the inverse of a matrix, we assume the matrix is square. A square. The size is n by n matrix. Then the following statements are equivalent. What it means? The following statements are equivalent. That means, okay, let me put a remark. That is, the statements, the following statements are either or true or false. Yeah, that is the meaning of equivalent here. Okay, now, okay, there are there were 10 statements. Number 1, A is an invertible matrix by the theorem in topic 2 today. A is invertible if and only if A can be reduced to identity matrix. Yeah, this is from the theorem in topic 2 today. Okay. So yeah, this statement is equivalent to the following statement. A is row equivalent to the n by n identity matrix. Yeah, here, row equivalent. That means that we can perform a sequence of row operations on A and reduce A to identity matrix. Yeah. So yeah, these 2 statements are equivalent. Yeah. If statement 1 is true, then statement 2 must be true. Okay. Number 3. If A can be reduced to identity matrix, then A has all the columns of matrix A are pivot columns. All the columns contain pivot number. But because A is square and the size is n by n, so A has n pivot positions. Yeah. All right. A has has n pivot position, then we have the linear system, the equation AX is equal to 0. Yeah, this is a matrix equation. Matrix equation is a linear system. Yeah, now A has n pivot positions. So all the columns are pivot columns. So this linear system has no free variable. All the variables are basic variables. So the equation has only the trivial solution. Trivial solution means zero solution. Only has zero solution. No non-zero solution. No non-zero solution. Number 5. This equation has only zero solution. If I recall that a matrix times a vector is by formula. A matrix times a vector is a vector. The vector is a linear combination of the columns of the matrix A. A times X is 0. If I write the right side is the right side actually is x1. X1 is the first entry of the vector X times first column plus x2 times second column. Here I assume A is n by 1, so xn column an is 0. This equation actually is this equation. Now this equation has only trivial solution. Then the columns of A form a linearly independent set. What is a linearly independent set? You need to go back to the definition of linearly independent set. A set is a linearly independent set. You need to solve this equation. If this equation has only trivial solution, then the set is linearly independent set. But of course, from statement 3, we assume this equation has only trivial solution. So therefore, this equation, vector equation, has only trivial solution. Therefore, the columns of A form a set. The set is linearly independent set. Let me stop here. There are still other 5 statements, but next time, okay? I don't have time, okay? Let me stop here.